All right. Good morning, good afternoon, and good evening, everyone. Thank you for coming today to the point distribution webinar. Just a quick reminder before the talk that we also have a talk this Friday by Julian Hofstadler. But for today, we have Lewis Brown from Yale University talking about positive definite functions, exponential sums, and the greedy algorithm, a curious phenomenon.
Thanks for the introduction, Ryan. So I'm going to start by setting up the big picture of what we're going to do today. So let f of x equal x squared minus x plus 1/6, a function on the torus, identifying 0 with 1 on the real line. So this is a graph. It's just a parabola, nothing exciting there. And we're going to define a sequence of points by starting with an arbitrary initial set, x1 through xm, in the unit interval. And then we're going to greedily set xn, the new point, to be the argmin over the sum from k equals 1 to m minus 1 of f of x minus xk. So we want the point that minimizes this function for all of the points we've picked so far, the xk. This might seem like a weird algorithm, maybe strange or a little bit arbitrary, but it has really remarkable distribution properties that we're going to explore throughout this talk. So let's look at what happens if we run this algorithm with the initial set of just the point 0. So we start with f of x minus 0, or f of x, the same picture we had before. And now we're going to find the x value that minimizes this function, which we can see is 1/2. So now we have f of x plus f of x minus 0.5. And now we need to pick a point that minimizes this function. And we have two options here, but it doesn't matter which one we pick, so we can just arbitrarily choose the left one, 0.25. And now we have the function f of x plus f of x minus 0.5 plus f of x minus 0.25. And to minimize this, we only have one choice now, which is x equals 0.75. So our sequence is going to start like this. And you can see that it's doing something really nice here in sort of filling in the gaps in any large intervals where it's missing. So the points are very well distributed. So this is going to produce an extremely regular sequence. So before I go any further, I want to rewind a little bit and just give an overview of the talk structure so you know what's coming. So I'm going to start out by introducing two friendly sequences, which we can use as references to compare the sequences we're looking at against. Then I'm going to introduce various notions of regularity, so we know what it actually means for a sequence to be regular and how we can quantify that and think about it. Then I'm going to introduce a fun game we can play to create sequences. Then I'm going to describe the curious phenomena that occur with these sequences and try to look a little bit about why those are happening. And finally, I'm going to look at generalizations to higher dimensional spaces. What can we still make work there? What kind of results do we get? And what changes? Okay, so first we have our two friendly sequences. So we're going to introduce two very structurally different examples of sequences. The two competing examples are, one, the Kronecker sequence, which is given by xn equals the fractional part of n times root 2. So we're just taking multiples of square root of 2 mod 1. We're just throwing away the integer part of that number, and we're going to get a sequence in the unit interval from 0 to 1. And we could really replace root 2 here by any other number with bounded continued fraction expansion. So it's not that root 2 has some magical properties we're taking advantage of here. It works for many numbers. And the other sequence is the van der Korpet sequence, which is given by taking xn to be the rational number, whose binary expansion is the reverse string of bits when n is written in binary. So what does that mean? Well, the first binary number is 1, so I'll write 0.1, or in decimal, 0.5. The next binary number is 10, so when I reverse that, I get 0.01, which is 0.25 in decimal. Then we have 11, which becomes 0.75. Then we have 100, which becomes 0.001, which is 0.125. And then we have 101, 0.625, 011, which is the reverse of 110, 0.375. And then we're going to have 0.111, which is 0.875, and so on. And here we can replace base 2 with any other prime base. So it's not that 2 is special, but that's just the sequence that we're going to be looking at in this particular case. So both of these sequences were cooked up, specially built to be optimally regular, but in a very different way. So let's take a closer look at what each of these sequences are actually doing. The Kronecker sequence, defined by xn as the fractional part of n root 2, where this is taking the number mod 1. So what is that doing? It's using irrational rotations on a torus to produce uniformity. So if this is the unit circle, the first point is going to be a root 2 rotation. So we start at 0, and then root 2 is 1.4. So we wrap all the way around, and then almost another half. Of course, we could also just do the 0.4 part alone and ignore the integer part. Then the next point, we're going to rotate that the same amount around the circle. And the next point, we're going to rotate this around the circle. We're going to rotate that around the circle. X4 rotates to X5. This rotates to X6, and this rotates to X7. So this is the first 7 terms of the Kronecker sequence. And because root 2 is irrational, we know it's never going to come back to a point it's already seen. So this is going to be a very regularly distributed sequence. On the other hand, the van der Korpet sequence, which is defined by taking xn to be the rational number whose binary expansion is the reverse string of bits of n written in binary. So if we look at the first 7 terms of this, we start in the middle, then we fill in 1/4, 3/4, 1/8, 5/8, 3/8, and 7/8. So this, we can see it's very well distributed across the unit interval, very evenly spaced, and we'll look more at that later. So this uses the regularity of binary expansions of numbers to produce uniformity. And it's sort of greedily filling in the gaps. At each step, it's placing a point at the midpoint of the longest empty interval. So it's saying this is very long and it doesn't have any points in it. Let's put a point in the middle of that. So our points are nicely spread over the interval. But now we need to say, what does it actually mean to be optimally uniformly distributed? What does it mean when I keep saying that these sequences are really regular? How do we quantify that? So I'm going to introduce a number of different quantitative approaches to measuring the regularity of sequences in the unit interval. These I'll refer to as combinatorial, analytical, numerical, and geometric. And I want to say right now that you do not need to memorize these notions. There's going to be a lot of information contained in each of these, but it's not like you need to memorize the definitions that I'm going to use again later. In fact, all of these notions are, in a very loose sense, equivalent. They're optimizing for the same thing. And this is why the Kronecker and van der Korpit sequences are able to perform optimally on all of them simultaneously. So if these were sort of substantially different measures, then being the best at one wouldn't allow you to also be the best at the rest of them. But the fact that Kronecker and van der Korpit sequences are both optimal on all four counts means that they're basically telling you the same thing about the sequence. Okay, so what is this combinatorial regularity? We want that for every natural number n, the set x1 through xn has the property that for every interval j in 0, 1, the number of elements in j is the length of j times n with a very small error. So we're just saying that of the first n terms, the portion of them inside of any subinterval j should be the right amount. It should be proportional to the length of j. We want the correct number of points to be placed within each subinterval. So for instance, if we look at the first 7 terms of the van der Korpit sequence and look at the interval j equals 0, 1/3, then we see 2 of the points are inside there. So 2/7 is close to 1/3. Of course, we can only get so close with a small number, but we want that as we drop more and more points of our sequence on the line, that we get really close to having the correct proportion of the points in each subinterval. Okay, then we have an analytical definition coming from Erdős-Turan, which is that we want the sequence to have the property that the first n terms satisfy favorable exponential sum estimates on expressions of the form sum of 1/k, sum of e to the 2 pi I k xl, and sum 1/k squared times the sum of e to the 2 pi I k xl squared. Basically, we just want that this exponential sum is small for small values of k. So if we take e to the 2 pi I k xl for the first n terms of our sequence, that should stay small. And what does this actually mean? Well, this is just taking our sequence and wrapping it around the complex unit circle. So we're saying that if it's well distributed, then these are spread out in a nice way, that when we add them up, we'll get lots of cancellation and we'll end up with a number with small norm. And what this k is doing here is saying that it's not just if we wrap our sequence around the unit circle once, but if we stretch out the interval and wrap it around twice or 3 times or any number, then we still want it to be the case that for small values of k, it has good cancellation. Now it might seem like for a general sequence, it would be difficult to compute these exponential sum estimates. But for the Kronecker sequence, it's actually very easy to compute just because of the way the sequence is defined. So if we try to write this exponential sum for the Kronecker sequence, then we would have sum from L equals 1 to n of 2 to the pi I k L root 2. Notice I don't need the fractional part in here because this exponentiation is doing the work for us, since any integer part is just a full rotation around the circle, which gets ignored. And what is that sum? Well, we just have to remember back to high school. This is a geometric series. So we have 1 minus r to the n over 1 minus r. So it's very easy for us to say what that is. And in particular, if we look at this number, the numerator has norm at most 2 by the triangle inequality because we have 2 things of norm 1. And so the problem really reduces to bounding the denominator. And we chose root 2 because it was badly approximable. This is equivalent to the thing I said before about it having bounded continued fraction expansion, which means that integer multiples of it don't get too close to integers too quickly. So it's hard to approximate with rational numbers in the sense that for small denominators, we can't get too close to root 2, which is the same as saying that the denominator of this fraction doesn't get too small too quickly, because this is precisely measuring the distance of a multiple of root 2 from an integer. Because if it's an integer multiple up here, then we're going around the circle an integer number of times, and we'll get exactly 1. Okay, now let's look at the numerical sense of regularity coming from Cox Maloft. So we want the set x1 through xn to be a good set for numerical integration, meaning that we want it to be that the integral from 0 to 1 of f of x dx is approximately equal to 1 over n times the sum from k equals 1 to n of f of xk, with a small error for smooth functions f. We'll make this more precise later. So we want it to be that we can approximate the integral very well just by looking at our points and averaging the value of the function over them. So this is a very relevant sense for applications where taking an integral is often computationally expensive or even impossible, and we really need to instead just pick a good sampling of points to try to average. So for example, if we use the function f of x equals x and the first 7 terms of the van der Korpe sequence, we would have 1/7 times 1/2 plus 1/4 plus 3/4 plus 1/8 plus 5/8 plus 3/8 plus 7/8. And because of the symmetries of the van der Korpe sequence, this is all going to average out to exactly 1/2, which is what we want because the integral of x is x squared over 2, which evaluated from 0 to 1 gives us 1/2. So this integrates f over the unit interval exactly, and the van der Korpe is doing a good job of numerical integration. And then we have the geometric sense of regularity, which is that if we take the 2-dimensional set, I over n comma xi, this is uniformly distributed in the unit square. So we're just taking our sequence and we're lifting it from the unit interval to the unit square using evenly spaced x coordinates. And we want it to be that every Cartesian box, AB cross CD, contains roughly b minus a times d minus c times n elements with small error. So this is saying a very similar thing to the combinatorial setting, that we want each box to have its fair share of the points in the sequence. It's very closely related, and it's actually sort of a trick to lift that definition up another dimension. So here's a picture of the first 100 terms of the van der Korpe sequence mapped onto the unit square like this. And we see that they're very, very uniformly distributed. So they're very nicely spread out over the square. There's no big regions that are missing points. Okay. So now we're going to give a quantitative measure of the combinatorial sense. And we define the discrepancy d sub n of a sequence by the supremum over all subintervals j and 0, 1 of the number of terms of the sequence in the first n that lie inside j divided by n minus the length of j, sorry. So we're just saying what's the difference between the number of points that it should have based on its length and the number of points that it actually does have in the first n terms of the sequence. So the discrepancy is the largest error of any interval after n terms in terms of how many points it has inside of it. And trivially, we have that the discrepancy is at least 1 over n for all n in any sequence. And the way we can see this is if we make a very small interval around the point x1, so x1 minus epsilon comma x1 plus epsilon, and we let epsilon go to 0, then all of these intervals contain at least 1 point. It might be that our sequence is sort of doing a bad job of being regular and pick the point x1 multiple times, but this certainly contains at least 1 point while it has arbitrarily small length. So up here, this would be at least 1 over n, and this is going to 0. I had originally written here the degenerate interval from x1 to x1, but I was worried there would be some purists who would call me out on that and be unhappy. So this is a proper interval. So then the question naturally arises, can a discrepancy asymptotically on the order of 1 over n be achieved? We know that it has to be at least 1 over n, and can we really get it to be exactly that, or at least that up to a constant? Well, if we look at the Vender-Corbett sequence, we notice that after 2 to the n terms, it's always perfectly uniform, because after 2 to the n terms, it just has all of the rational numbers whose denominator is 2 to the n. So it definitely attains this bounds when this big N equals a power of 2. But what about in between? In between powers of 2, we're going to accumulate a logarithmic error term while it's still taking the time to fill in all of those gaps. So what we want to know is, can any sequence beat Vender-Corbett and remain uniform even while still filling in those gaps? And Johannes Vender-Corbett himself was the first one to pose this question. Can anyone beat my sequence? And the question was first answered by Tatiana von Arden-Ehrenfest in her 1945 paper, Proof of the Impossibility of a Just Distribution of an Infinite Sequence over an Interval. And if it's not clear from the title of the paper, the answer is no, it's not possible. In particular, 27 years later, Schmidt gives us a theorem that has a nice bounds on what the discrepancy can actually be, telling us that for any sequence, there's always infinitely many integers n, such that the discrepancy of the first n terms is at least 1 over 100 times log n over n. So we're always going to get a logarithmic error term infinitely many times. We can never get down to the order 1 over n. And I mentioned before that Kronecker and Vender-Corbett are both optimally regular in all of those senses. So in particular, they achieve this lower bounds up to some constants. So now let's present a fun potential theoretic game. We start with a set of electrons, which all have equal negative charge. And a pair of electron at points x comma y will generate a potential of 1 over the distance between x and y. This is Coulomb's law from physics. And now we want to pick a new point to add an electron to by minimizing the energy of the system. So you can think of this as minimizing the work we have to do to keep that system in place. The electrons are trying to repel each other and push each other away, and we want to minimize the amount of work we have to do to hold them still. So the function we're minimizing is f of x equals the sum from I equals 1 to n of the distance between x and xi to the minus 1. This is just the sum of the potentials between x and each existing electron, the effective potential. So visually, we can imagine there's a little shifted 1 over absolute value of x function placed over each point. So if we have a point charge placed at 0.2, 0.6, and 0.45, then each of them carries a potential like this. And then if we add those up, we get this orange curve, which is the effective potential of whatever new point I'm going to place. So we want to minimize the orange curve. And some of you might be looking at this and scratching your heads a little because the question I just posed doesn't make any sense. F doesn't have a minimum because that orange curve is going to 0 as we go further and further out from our existing electron charges. So it doesn't even have a minimum. We just get as small as we want by going arbitrarily far out. So in order to resolve this, we're just going to play this game on a circle instead. A circle is compact, so we know that the minimum always exists, and it's got some nice symmetry we can use to actually analyze what happens here. So let's go back to our function from earlier, the second Bernoulli polynomial, which is defined by x squared minus x plus 1/6 on the unit interval, identifying the circle with 0, 1. And we're going to define a sequence of points starting with an arbitrary initial set, x1 through xm, And then we greedily set xn to be the argmin of the sum from k equals 1 to n minus 1 of f of x minus xk. So this is just finding the point that minimizes the energy, except instead of using Coulomb's law for the energy, we're using this function. And the resulting sequence is going to have just remarkable distribution properties. So what's the intuition behind this? What is this function actually doing? Well, this is adding horizontal shifts of f of x together. F of x minus xk is just taking f of x and shifting it xk to the right, collecting it in an aggregate function, f sub n of x, the sum of all of these so far, which is filling in the gaps. So by picking the argmin to shift by next, we're adding a function that will push up the value at the lowest points and smooth out the aggregate. So we're trying to get a smooth, effective potential function so that we can keep the energy of the system low. So let's look back at our example from the beginning again. So if we start with just the singleton set 0, then we first add a point at 1/2. This minimizes the energy. Then we can pick 1/4. Then we pick 3/4. And then we can pick any of these 4 points. So each time we're just adding in the shifted parabola, and it's balancing out some of the variation in this function. So Florian-Posinger has a theorem which tells us that this is actually always going to give us the van der Korput sequence if we start with a singleton set and a nice function f. So specifically, if f satisfies f of 1 minus x equals f of x, so f is even, and the second derivative exists and is positive on the open unit interval 0, 1, then the greedy algorithm running on f and the initial set 0 will always yield a van der Korput sequence. And here I say a van der Korput sequence and not the van der Korput sequence because of course we had some arbitrary choices where we had multiple minima and we just picked one, but we'll always get a van der Korput sequence and we can pick the points in such a way that we get the traditional one if we want. But even if we just start with 2 elements, we don't know what the sequence will look like. But we can do some analysis on it to bound the discrepancy. So here's another theorem from Posinger, which says that if f is bounded and symmetric about 1/2, and further we have this quantitative positive definite condition, which is that the Fourier coefficients are at least c over k squared for all non-zero k and some positive c. Then all sequences defined by this greedy algorithm on an arbitrary initial set will satisfy that the discrepancy is at most some constant over the cubed root of n. Where this constant just depends on the initial set. And this is the paper where both of these theorems are from, and it's blue because I made it a hyperlink, so if you want to look through the slides later, you can just click on this and it will open up the archive paper. Greedy energy charges can count in binary, point charges in the van der Korput sequence. We're going to come back to this later to show the proof, but we need to build up some machinery first, but it's a very slick proof. So how does the discrepancy of these sequences compare with van der Korput numerically? So here's a graph. If we run our algorithm on the points 0, 1, 3 versus the van der Korput sequence, which remember is just running the algorithm on the point 0, and the discrepancies are decaying at exactly the same rate. They're right next to each other. What if we tried something weirder? Maybe there was something nice happening with 0 and 1/3. There were some special symmetries going on there that made things balance out. Let's try it with 0, 0.1, and 1 over pi. Nope, it's the same picture. We still got this really nice decay, that's on par with the van der Korpit sequence. And remember from earlier, the van der Korpit sequence has the optimal discrepancy up to constants. But what if we try to mess it up in the middle? What if we let this algorithm run for a while and then throw in some points that are all close to each other so that the discrepancy will shoot up? So here we're going to run the algorithm on 0.6 for 50 points. Then we add 0.5, 0.51, and 0.52. So these are all packed around 1/2, and the discrepancy shoots up. We have too many points concentrated in the middle of the unit interval. But then we run the sequence for another 100 terms, and very quickly it gets back down to the level of van der Korpit. And even at the end here, it's a little bit below. So even if you try to interfere, you really can't mess this algorithm up. It fixes itself if you attempt to. So maybe the Bernoulli polynomial is just a fluke. Let's try it with another function. This time we'll use f of x is minus the log of 2 sine pi of x, 2 sine pi x, which has Fourier series, sum of 1 over k cosine 2 pi kx, or in complex terms, we have 1 over 2 absolute value of k e to the 2 pi I kx. So this is just the Green's function of the fractional Laplacian. We still get the same picture. So it doesn't actually matter what function we use, we're still going to get this really nice discrepancy curve that goes right next to van der Korpit. So now let's talk about the curious phenomena of these sequences. We conjecture that for all initial sets, x1 through xm, and all even f, with f hat of k is greater than c k to the minus 2 for all non-zero k. Remember, these were just the conditions for Poslinger's theorem earlier, that the greedy algorithm, xn equals argmin sum from k equals 1 to n minus 1 of f of x minus xk, will always produce a sequence such that this double sum over k and l going from 1 to n of f of xk minus xl is at most on the order of log n. So this is looking at the, this is the total potential of the system once all these electrons are placed, what's all of the potential interactions between them, but it also contains some extra terms from when these points are the same. And we'll look more at that later. And Pornov showed that this is optimal, so no sequence can do better than log n. Okay, and we also conjecture that for all initial sets, x1 through xm, and all even f, such that f hat of k is greater than c over k squared for all non-zero k, then this greedy algorithm will produce a sequence such that the L infinity norm of this function, sum from k equals 1 to n of f of x minus xk, the effective potential function, is also going to be order at most log n. And we really suspect that both of these are true based on all of the numerics, but the results we can prove are much looser bounds. So these are very much open problems. So let's look a little bit more at this. If we let f sub n of x be the sum from k equals 1 to n of f of x minus xk, well, the L infinity norm of f of x minus xk is going to be the same of the L infinity norm of f of x. This is just saying that the maximum value of the function is the same if you shift it over a little bit. So we definitely have that the L infinity norm of f sub n is at most on the order of n. Right? You can imagine that if each of these f's has maximum value 1, then when we add them up, we're going to get at most maximum value n. If it happens that all of those maxes are at the same points, but it won't because we're shifting them. If we want to make a stronger claim, we're going to apply the Cox Maloft Inequality, which will bound the error of numerical integration. So let's look at what that says. This is a theorem from Cox Maloft in 1942. So we need a function f with finite total variation, where total variation means the integral from 0 to 1 of the absolute value of f prime of x dx. Another way to think of this conceptually is just that if you project your curve onto the y-axis, this is how much the height goes up and down as you traverse. X goes from 0 to 1. And if we have any set of points, s equals x1 through xn, then we're going to have that the average of the values of f over the points xi minus the integral from 0 to 1 of f of x dx. This is at most the variation of f times the discrepancy of the set S. So remember, this is the numerical integration we saw earlier, and this is the extra condition we need for it to work, that f has finite total variation. Okay, so now we need to figure out how can we apply this to our setting. So here's the inequality again. And first, let's note that our function f of x equals x squared minus x plus 1/6 is mean 0. So if you integrate this from 0 to 1, you're going to get 1/3 minus 1/2 plus 1/6, which is 0. And in fact, whatever energy function we have, we can always shift it up or down to be mean 0, and it won't affect the algorithm because this is a minimization process. So if we have f of x plus 5, we're still going to have our minimum at the same x value. It will just change the y value of what that minimum actually is, but we don't care about that. Thus, the integral of f is 0, and the inequality simplifies to the absolute value of 1 over n sum from I equals 1 to n, f of xi. So this is at most the variation of f times the discrepancy of s. Now the variation of f is a constant in the sense that it only depends on f. It doesn't depend on the set of points we're looking at. And further, since discrepancy is translation invariant, meaning if we take our set of points and we rotate it around the circle all by the same amount, the discrepancy is the same. So we have the discrepancy of x minus x1 through x minus xn is the same as the discrepancy of x1 through xn. So it doesn't make a difference. We're just subtracting x from all of these, and then we're multiplying by -1. So it's also going to be a reflection invariance, right? So because of that, we don't care at all what x value we're evaluating on. We have the same discrepancy. So the inequality tells us that the L infinity norm of Fn, which is the sum from k equals 1 to n, f of x minus xk, well, now I can put an n on the outside and a 1 over n on the inside. And so it's telling us that this expression, that's the numerical integration, is bounded by the variation of f times dn, but we don't care about the constant there, so that's just saying it's bounded by n times the discrepancy of those points. And Schmidt from earlier told us that the discrepancy bound is at least log n over n asymptotically, which means that when we multiply by n, this bound is at best log n. So our conjecture is saying that this optimal bound is actually achieved in our setting, that this log n, which is the strongest this bound could be, is precisely what we get for this L infinity norm. And if we look at the empirics, the L infinity norm is extremely small in n, with the L infinity norm of f sub n barely exceeding the L infinity norm of the original function f. So here's a picture of the functions f100, f110 through f200, and we see that there's no obvious discernible pattern in what these functions are doing, but that they all stay sort of small, that even though we're adding up 200 different shifted functions, they're canceling in some really nice way, that the maximum and minimum values are not much more than the original function. So somehow these shifted functions are balancing out very nicely in a way that cancels and keeps the energy of the system low. In fact, the sequences defined by this algorithm appear empirically to be competitive with the van der Korput and Kronecker sequences, which, remember, we know are optimal on all of those notions of regularity that we discussed at the beginning of the talk. Combinatorially, analytically, numerically, and geometrically. But a proof is evasive, and it's an open question whether or not they truly are. We really don't know how to show this, but it really seems like it's true. Okay, now we're going to return to our proof of Possinger's theorem, but we need to define one more thing first. So note that we can turn our sequence into a measure by setting mu sub n equals 1 over n times sum from k equals 1 to n of delta xk. So we're just putting a Dirac measure on each of our first n points, and then we're scaling it down by n so that it's a true probability measure. It has total mass 1. Or in other words, we're placing a point mass of weight 1 over n on each of our terms in our sequence. And we define Zinterhoff's diaphony of the measure, f sub n, as the sum over all non-zero k of the kth Fourier coefficient squared divided by k squared, and then we take that whole sum to the 1/2. And for analysts who are more familiar with Sobolev spaces, this is the same as just the Sobolev -1 norm of mu. And yeah, this is really just because these terms are coming from different backgrounds. So if you're in number theory or combinatorics, you would think of this as diaphony, whereas if you're coming from an analytical or PDE background, you would say that's the Sobolev norm. But they're the same thing. And if you don't know what the Sobolev norm is, I'm not going to use anything fancy about Sobolev spaces in this talk, so you don't need to worry about that. We just need to know this one definition of what the norm is, which is this. Okay, so we're going to now present the proof of Possinger's theorem. So let me just restate the theorem so we know what we're proving. We have a function f, which is bounded, symmetric about 1/2, and the Fourier coefficients are greater than c over k squared. And we're saying that all sequences defined by the greedy algorithm on an initial set satisfy that the discrepancy is at most some constant over the cube root of n. Okay, so let's start the proof. We can assume without loss of generality that f is mean 0. So remember we said before that we can always just shift our function up or down to be mean 0, and it won't change the algorithm. Then if we look at this double sum over m and l going from 1 to n of f of xm minus xl, then we're going to get n diagonal terms when m equals l, which will all be f of 0, so n times f of 0, plus 2 times the off-diagonal terms, the sum from ml equals 1 to n, m less than l of f of xm minus xl. And the reason I can make this a 2 is because we're assuming our function is even. So f of xm minus xl equals f of xl minus xm. So we're just assuming that m is less than l, and sorting the terms that way. And then I can just rewrite that sum as the sum as l goes from 2 to n and m goes from 1 to l minus 1. And I claim that this whole expression is at most n times f of 0. So why is that? Well, by definition of the greedy algorithm, this sum is going to be the minimum over all x of the sum from m equals 1 to l minus 1 of f of x minus xm, right? We chose the point xl specifically to be the point that minimizes this expression. And in particular, the minimum of this function is going to be less than the average. And since we know that that f is mean 0, all of the shifts of f will be mean 0. And so this sum of shifts of f is also going to be mean 0. So the average is 0, and the minimum has to be less than that. So we know the minimum is negative. But this is actually the only point in the whole proof we're going to use this minimum. And all we're using is that it's less than the average. So we have a much stronger condition here, and we just don't know how to use it. So if there's any other algorithm that also picks points to give a value here less than the average, they'll work just as well for the purposes of this argument. Okay, so just writing this inequality again, we have that the sum of f of x m minus xl is at most n times f of 0. And I'll call that diamond. On the other hand, we can take that same sum and expand it using the Fourier coefficients. So we have the sum over all integers k of f hat of k times the sum as m and l go from 1 to n of e to the 2 pi I k xm minus xl. I can split up this sum of products into a product of sums, because remember, e to the 2 pi I k xm minus xl is the same as e to the 2 pi I k xm times e to the 2 pi I k minus xl. So I can split those up. And then this minus in the exponent is really just conjugating this whole expression. And so when I multiply this number by its conjugate, I get the norm squared. So I get this. So just combining with diamond from the previous slide, we have that this is less than or equal to n times f of 0. So this also is, because they're equal. Okay. And now we have to use our final condition that the Fourier coefficients are at least c over k squared. So we can just use this directly here. We have n times f of 0 is at least this expression, and then f hat of k is at least c over k squared. And in the same step here, I wrote an n squared on the outside and put a 1 over n on the inside, which is squared, so those will cancel out. And then I can plot the c, and this expression on the inside is precisely going to be the square of the diaphony that I mentioned earlier, or the -1 Sobolev norm. So this whole thing is c n squared times the Sobolev norm of mu n squared. In particular, if we divide by n squared and we solve for this, we're going to get that the diaphony is at most on the order of the square root of n. We're throwing out the constants because we don't really care about them. And then finally, by Levesque's inequality, we can bound the discrepancy, as discrepancy is at most on the order of diaphony to the 2/3, which is at most on the order of n to the -1/3. We're just taking n to the -1/2 to the 2/3 is n to the -1/3. And that's what we're trying to prove. So we have the desired result. Okay, now we're going to talk about how we can do this on higher dimensions. So if we want to minimize energy on a higher dimensional manifold, it's going to be much harder. The setup is the same as before. We want to place point charges so that the total energy is minimized, meaning that each charge should be far from the others. And this is sort of a regularization procedure, because it means that the charges won't be too close or they would repel each other and have higher energy. So a common energy function to use is the Riesz kernel, defined by k sub s of xy is minus log of the distance between x and y, or the distance between x and y to the minus s. And it's known that the minimizers of the Riesz potential are optimal with respect to the Sobolev minus d over 2 norm from Marzo and Mas 2019. And we also know that they're uniformly distributed with respect to the Hausdorff measure, which is referred to as the poppy seed bagel theorem from Hardin-Saf 2004, so-called because you could use it to think about the distribution of poppy seeds over a bagel, a 2 torus. And we also know that the minimizers of the Green's kernel are asymptotically uniformly distributed. This is a result from Beltran, Corral, and Criado del Rey in 2017. So people have studied this. The problem on the sphere with Riesz kernel distance to the -1 actually dates back to physicist J.J. Thomson all the way in 1904. But to this day, over 100 years later, we still only know the solution for a handful of cases. So here's an image from Wikipedia of the solution for n equals 2, 3, 4, and 5. And in these 4 cases, we're able to solve the problem only because there's some nice geometric figures that we can make with lots of symmetry. But in almost all cases, we still really don't know how to do this. So if even the sphere poses a challenge, how could we ever hope to solve this on a general manifold? Well, maybe we can play the same type of game as before and greedily pick the best point at each step. We're not going to get a global minimizer, but maybe we can get something that asymptotically has the same sort of behavior. This has been researched, and greedy sequences constructed this way with any kernel are called Lea points. So if you look at this paper from Lopez Garcia and Wagner, there's a wealth of results on the one-dimensional circle alone. That whole paper is all just on the one-dimensional circle, and there's a lot to say there. It's not an easy case. So let's set up our algorithm again. We have a manifold M, smooth and compact with no boundary. And we're going to let g of xy be the Green's function of the Laplacian, which satisfies this equation. And Green's kernel behaves similarly to Riesz kernels. In dimension 2, it's comparable to k sub 0, the minus log Riesz kernel. And for dimension at least 3, it's going to be on the order of k sub d minus 2. So that's the distance to the 2 minus d, which is sort of the best Riesz kernel in dimension d. But unlike Riesz, Green's kernel is intrinsic, and it doesn't depend on the embedding of the manifold. So it's an intrinsic property the manifold holds. And so now we can define our sequence greedily by xn equals the argmin over x and m of the sum from k equals 1 to m minus 1 of g of x comma xk. So instead of f of x minus xk, now we're using g of x comma xk. And the scaling of the proof is going to be fundamentally different in higher dimensions, and it will give us stronger bounds, actually. But to look at that, we're going to first need to look at the Bosserstein distance. So the Bosserstein distance, which is also known as the Earth mover's distance, measures how much work it takes for us to carry the mass of one distribution to another. So, for instance, if we want to transport a point mass of weight m by a distance of epsilon, we're going to incur a cost of m times epsilon. So this really is just reflecting the physical concept of work. It's weight times distance. So it's very much what our intuition tells us it should be. If we look at another example, here we have a point distribution. We have 2 point distributions, one for each color, where each point has weight 1/2. And I want to know the Bosserstein distance between the blue and the red point distributions. So the most efficient way for me to move the red mass to the blue mass is to take the weight on point 1 and move it to point 2, and to take the weight on point 3 and move it to point 8. So that distance would be 1/2 times point 1 plus 1/2 times point 5, which is point 3. I'm just taking the weight times the distance I have to carry it. We could also think of this in a 2-dimensional setting. Maybe we're transporting a point distribution between stores and houses. So each store has some distribution of food. Each house needs some distribution of food. Some stores have more food, some houses need more food, and we need to send trucks around to deliver the food from the stores to the houses. So it could be some complex diagram where each store needs to decide how much of its food to send to each nearby house. And we want to know how much total driving has to happen in order to achieve this. But in our setting, every point on the unit interval is going to have a house. And we're interested in measuring the Bosserstein distance between the point measure mun from our sequence and the uniform distribution dx. So this is the point measure where we have a point mass at each term in our sequence of the first n terms, and the uniform distribution if everything was truly uniformly distributed over the interval. So here's the van der Corput sequence mapped to the unit square again. And we could imagine we want to take the Bosserstein distance between the normalized sum of Dirac measures on these points and the uniform distribution on the unit square. So on each of these points, I have a little point mass of weight 1/100, so that the total mass is 1. And I need to push that mass around so that I completely smoothly cover the square. So we would need to sort of smudge each point to transfer its mass continuously over the nearby points. And the W1, the Bosserstein distance, measures how much smudging do we need to do. So formally, I have to write the actual definition somewhere, the equation. The p Bosserstein distance between two measures mu and nu is defined as this infimum, where this is the metric on the space. Gamma is the collection of all measures on m cross m with marginals mu and nu, also called the set of all couplings of mu and nu. So we're just integrating over all transport methods the cost it would take. And in 1D, we have that the Bosserstein 2 distance between mu and dx, the uniform distribution, is at most on the order of the diaphony. So it seems like W2 is a good generalization of diaphony to higher dimensions, because this quantity is not going to be well defined in higher dimensions, but W2 still is. So for any d-dimensional manifold M, there's some constant c greater than 0, such that for any set of n points on M, we have that the W1 distance between the point distribution and the uniform distribution is at least c times n to the minus 1 over d. So this is a lower bound on the Bosserstein 1 distance. And the proof is really easy. This is just a basic observation about scaling in d dimensions. You can imagine placing balls of radius r equals epsilon times n to the minus 1 over d around each point xi. So the total volume of the balls is going to be at most n times the volume of each ball, right? This is the best we could do is if the balls don't overlap at all. So we have n balls and the volume of each is omega d times r to the d, where omega sub d is some constant that only depends on the dimension. So for instance, in 2 dimensions, we have pi r squared. In 3 dimensions, we have 4/3 pi r cubed. So wd is just some, omega d is just some constant, and we don't actually care what it is. But the point is that the volume will scale at the rate of r to the d. So in particular, if we're setting r equal to this, that becomes epsilon to the d times n to the minus 1. And the n to the minus 1 on the inside cancels with the n we're multiplying it by on the outside. And we just get omega d epsilon to the d.
Louis,
Yep.
sorry to interrupt here, but at this point we're getting close to, we're a bit past the 50-minute mark.
Okay. I'm sorry.
No, it's fine. Just if it'd be possible to wrap up.
Mm-hmm. Thanks. So we can pick epsilon small enough that this quantity is less than half the volume of M. And in particular, this would mean that we need to transport most of the probability mass a distance of more than epsilon n to the minus 1 over d. So that would mean that the Bosserstein distance is at least epsilon n to the minus 1 over d over 2. Because we need to transport most of the mass, at least this distance. So we have our bound. So if we look at this picture one more time, we could imagine this as a visualization of that proof, that each of the points is a very small disk, and the vast majority of the area is going to be outside of the disk. So we would need to do a lot of smudging in order to spread that point mass over the uniform distribution. Okay, so the theorem is that if we have a sequence obtained from this algorithm, then the Bosserstein distance between the point mass and dx is at most on the order of n to the minus 1/2 square root log n if d equals 2, and n to the minus 1 over d if d is at least 3. So this is really exciting because n to the minus 1 over d is the best we could have hoped for, which, as we just showed before. And if you're paying very close attention, you might notice that I'm cheating a little here because this is W2 and not W1. But by Holder's inequality, if W2 can't be better than W1, So the bound of n to the minus 1 over d is still the same. So this result is optimal in d at least 3, but we don't know what the best discrepancy is, or if this implies that the sequences obtain it. We just know that it's the optimal Bosserstein distance. So there's many open questions here. This is a completely new type of sequence. There's lots of mysteries, even just in the unit interval. It seems numerically to be optimal. So maybe such sequences are also optimal in higher dimensions. We know that they are for Bosserstein distance, but we don't know about discrepancy. And it's numerically challenging to compute in higher dimensions, so it's hard to get good empirics on this. Maybe it has nice connections to potential theory with Green's function. So lots of questions here. Maybe there's other types of functions that work. Maybe there's a whole other class of functions that produces even better algorithms. We don't know. So thank you for coming to my talk.
All right. Well, thank you very much for the talk. Do we have any questions from the audience?
Actually, I have a question, if that's okay. Hi, it was a beautiful talk. Thank you very much. And I was wondering, with respect to your potential theory stuff at the end, so these greedy algorithms, Leia sequences, potential theory. So suppose you have, in a more general setting, just even in RD, and you have a compact set where you're trying to minimize the Reese energy or Newtonian energy or something. Do your discrepancy results, are they valid there? Or do you really need to have a manifold in a nice setting?
So this particular theorem is just on manifolds with the properties that the Laplacian and the Green's function are going to have there.
Okay, thank you.
Other questions?
One quick question. I'm sorry if I just missed this, but the title said positive definite functions, and it wasn't quite clear exactly where the positive definite functions were appearing.
Right, so the positive definite was because we had a condition on our function f that we're using for the algorithm that the Fourier coefficients are at least c over k squared.
So it's well done from that. Okay, got it.
Definiteness.
Yes, speaking of manifolds and the green kernel, is the exponent in W2 tied into green kernel?
What do you mean?
Would you do WP using the same approach?
So the particular proof uses W2. I'm not sure if we could generalize that to WP using similar approaches. It's certainly a good question.
Any other questions for our speaker? All right, well, just in case, I'm going to stop the recording now in case anyone has questions that